All right. So I'm Shipra, and I work on reinforcement learning, multi-arm bandits, online learning, all those fields. And to me, when I first heard the presentations from Dream Sports, it was really interesting how many interesting problems, deep problems are here in this area. And we get to work with those problems and formulate new ideas and test new ideas in RL algorithm design. So the problem that I will present here is about contest design and catalog optimization. And many of you might already know what those words mean, but I'll just give a little bit of understanding of what I think it means, and you can correct me. So Dream Sports, as many of you know, is this platform where there are contests based on games, mostly primarily cricket, but other sports too. And participants is like a fantasy games where participants can participate, choose to buy tickets for any of these contests, and until there are spots left, and then they can win or lose based on what they predict or bet and so on. So the problem of contest design is very interesting because each contest in some sense is formulated just based on setting some parameters. So there is not really a physical good involved, just like there would be if you were designing a new product at Amazon or a new movie at Netflix. But that doesn't mean that it's you can just create as many contests as you want without any cost, because there's only limited number of participants. And if you create too many contests, then you would cannibalize one contest for another. And in some sense, the problem of contest design is inherently tied to the problem of recommendation, because if you create a lot of contests, but you never recommend half of them to your participants, it's almost as if you never created them. So if you create a contest, you better have a strategy to recommend it in order to get sufficient interest and participation. So that's why when I talk about these problems, I would not necessarily differentiate between design and recommendation of these contests, because design is inherently choosing these parameters that you want to launch a new contest on, but it has to be inherently tied with how you're planning to recommend them. Now, just as an overall problem statement, I have to kind of make the problem simpler and put it in the setting that I'm thinking about. Of course, there will be other aspects of it in the real world, which I hope to participate in very soon. So I'm thinking about a platform where we can see users coming in and observe what contests they are participating in, what is more popular, what's not, and we can see what they do in those contests, how frequently they interact with these things, in what ways they interact with these things. And the idea is to use reinforcement learning, which is a tool for handling sequential decision making where you don't understand the environment fully, in order to design new contests and recommend existing contests to these users. So if I just formulate it as a very traditional sequential decision-making problem, the idea would be you have this platform where users are arriving, not necessarily fully sequentially, maybe in parallel, but at least they're doing their activities sequentially. You can observe user state. And interestingly, and I'll talk more about this, the contest state. So by user state, I mean that based on what they have done recently, they are in different states. Because if are they experienced, or have they lost recently, have they won recently, how much have they interacted recently, are they tired? So that's user state. But there's also a contest state, which means is the contest being already popular, or is it just launched? How well is it being adopted? Is the contest being close to finish or not? So the contest is also dynamic, and I'll talk more about this, how this is so different from other recommendation, such that movie recommendation or product recommendation. And based on these observation, you want to make a decision about which contest to recommend. And in some sense, like mathematically, I personally don't feel there is a much difference between recommending a contest from a catalog or entirely new contest, because as I said, the recommendation and design is completely tied here. Now, based on what you recommend, you will see some interactions of the users, and then you can learn from those responses and keep doing this. So that would be your traditional sequential decision-making formulation. But interestingly, there is nothing traditional about this problem. There's so many interesting aspects, and some of which I have looked at in different contexts, and I would like to make some connections to those. How am I doing on time? Sorry. Okay. It's okay. I'll 1 minute. Okay, I'll just quickly go through some of these aspects. I should have warned, like 5 minutes is too less for someone who speaks for 3 hours every class. So one aspect that's very interesting is the non-IID response. And this is, although typical in reinforcement learning, that there is some state, and therefore the same decision has different response every time you recommend it based on the state. But one interesting aspect, which I haven't seen in something like pricing and product recommendation or movie recommendation, is this aspect that what you are recommending, the action, it itself has a state, right? The contest itself is different from the last time you recommended it, because now maybe there are more people in it, there's less spots left, and so on. So there is some connection to inventory problem where there is less inventory left, but not exactly, because there's also an aspect of many people being in it might actually make it look more attractive than less attractive. There's also imitation effect, and I looked at this for pricing and product recommendation, where there is this idea, and people use BAS model to model it, that there is this idea that when you launch a product, even though if it's expensive, a lot of people buy it, then other people also want to buy it, just because people like to imitate what's popular. And that gives you like a non-linear adoption of a product because popular things get more popular. So looking at that aspect, you can imagine that no, we cannot think about recommendation as being just one-time activity, which can get you some clicks. It also has a long-term effect of making that product, that contest more popular and launching it in a good way. And finally, with this aspect, which is incredibly interesting, is way to participate in this contest, how to get in, how to get out. And you can imagine any learning strategy we design, they will try to game it. And I have some work on this aspect in my auction design work. These are some references which are related to all these things I talked about, and I'll stop here.
I think we have time for one quick question, if anyone wants to ask. Please. Naman.
I don't want to join.
Yes.
I may not want to join a contest too many people are in
Yeah.
because I want to win
This
also.
is both related to the highly sophisticated users. So as I was saying, like as compared to inventory problem or something where there's also an anti-imitation effect, it's less stock left or something, maybe you don't want to try to buy it. But the strategy part is very, very interesting and deep, because we don't know exactly how users are deciding this. In fact, like I read some of these Reddit forums about it, and there is like very detailed strategies about how to start, and then which contest to start with, and then what to go towards. So this is a very interesting and important question as to understanding how users respond in long term towards these contests.
Thank you. Thank you, Shipra. And we'll go straight into our next presentation. It will be Seyoung Roh, who's a PhD student at the Department of Computer Science here at Columbia.
Right. Do you want to put this microphone? Huh? I can see here. Okay. Hold on. How about this? Okay, now I start. Hi everyone. Hello. Okay. Hi everyone. I'm Seyoung. I am a fifth-year PhD student at Columbia University here, studying computer science. And I am very honored to talk about my research in front of everyone here today. So let's begin. Imagine that we are watching an NBA game, maybe tonight. It's Knicks versus Celtics, and you are halfway into the game, wondering who is going to win in this game. To put this question in a more data science-y manner, I can say, in a partially observed game, can we predict the score trajectory for the rest of the game? This is an interesting question, not just for the men's basketball game, but probably for most of other sports too, right? But then how would a data scientist answer this question? So here comes my favorite method called synthetic control. Synthetic control is one of the popular approaches to answer that question, given that we have access to the previous game results. So I am going to construct a matrix that's showing each a team's game score trajectory in some game that's going to be the rows of this matrix. So the columns naturally represent the time, where the first column is the beginning of the game, and the last column will be the end of the game. So in the first row, I'm going to put this particular game, the team Knicks score trajectory that I have observed so far. And you will see here, little clock is where we are at right now. So we have observed everything up until this point. So left side of this, the first row, left side of this time clock will be fully observed. But then we'll have some missing values. It will be empty on the right-hand side. And the question is to fill that values by learning something from the rows below. And the rows below are some other team's score trajectory from some previous games. And how the synthetic control does is it's going to learn a linear relationship between this particular game, Knicks team's game score trajectory, and other teams' score trajectory from the previous historical games. So for example, I can say that the Knicks score trajectory so far could be like 20% of what other teams, like Chicago Bulls game trajectory, score trajectory from yesterday's game, and maybe 80% of Knicks versus Celtics Knicks games score trajectory from a year ago, something like that. And then we're gonna use this information to make predictions using the right half of the matrix to fill in that yellow blanks. So traditionally, the synthetic control algorithm worked on aggregate level observations, meaning that we can think of this score trajectory as aggregation of each individual player's performance in one game, right? But then my natural question was, what if we try to estimate not the whole team score trajectory, but like, what if I have access to each player's contribution to these scores? So now I have, in the first row, I have the points trajectory scored by Jalen Brunson, not the whole Knicks team. Yeah. And then I can construct similar matrix like this with the other players' score trajectories, right? But then this brings us interesting mathematical changes, fundamentally disrupt all the assumptions of synthetic control. And mainly, intuitively, we can see that the data matrix will be much bigger because we have a lot more players than we have the teams in NBA League. And then individual level observations are inherently more noisier, right? But they're not only cons, like there could be some additional information about the players that we can learn from some structure from and maybe use that to make a better prediction. So in a nutshell, in the near future, what I want to focus on in my research is how do we design an advanced version of synthetic control methods to make an individual level prediction. I saved a minute, and that was my presentation. Thank you.
Thank you very much. We'll have time for one question, I think, at least. Please.
Given that momentum in a game is such a big component, like score trajectory, usually in like, pro sports and stuff, have you ever thought about trying to quantify momentum in a game? So instead of looking at just like individual player statistics or data, also like looking at like game data or like where the trend is going for So yeah, my question, I guess, is just, have you ever thought about like using momentum and trying to quantify momentum to help with your research?
What do you exactly mean by momentum?
So, you know, when you're watching a sports game and one of the teams is on an upswing, they either have scored a lot in the last like 5 minutes. So like not momentum in like a physics sense, but like more in like a sports
Yeah,
sense, like
sure.
you're playing the game and your team has momentum, right?
Yes, there could be some more sophisticated methods that we can further develop on top of this. But basically, the synthetic control method's assumption is to pick up those momentum from the previous games and then learn from there. Does that make sense?
Okay, so no like live data, like you can't like stream live data of like the momentum of the current game that you're trying to predict necessarily. Like you're using past data of games, not like live data.
Past data, I mean like the rest of the matrix will be something from the past data. And then that kind of momentum could have happened in past historical games as well. And then this method is trying to pick up, oh, it's following this like momentous like stream of like upsurging scores from some other data. And it will show similar patterns. And then the method is going to pick up that.
Got it, thanks.
Thank you very much, Seyong. And for our next presentation, we'll have Priyank Agarwal, who's a PhD student here at Industrial Engineering and Operations Research. Thank you.
It's on my boy. You have a.
How can I bring this up? Do you want to start and I'll grab the PowerPoint?
Okay. Fine. I think we have some issues with the slides, but it's okay. So I'm Priyank. I'm a fourth year PhD student. I work with Shipra and okay, we have slides up. That's good. I'm honored to be here and thank you for setting up a good program. Let's talk about the slides. So I'm going to talk about some applications of reinforcement learning, specifically focus on off-policy evaluation and adaptive experimentation. Oh, there. Okay. Let's do it this way. Okay. So how does the reinforcement learning comes? So think about the user online platform interaction. In the reinforcement learning way, we would want to model the interaction as a Markov decision process. So think of the agent as the online platform, the actions as the features, products, or services provided by the platform to the users. The environment response would be the user response. And the reward could be the revenue. And state is slightly more nuanced. It could be some of the metrics that the platform cares for example, user properties, for example, churn rate for an online platform, and other things. And one thing to note that is online platforms log in huge amount of data. For example, I've been told Dream Sports, I think that data is quite stale. Maybe there's more than 35 terabytes of data per day for Dream Sports as of now. So off-policy evaluation, informally speaking, deals with techniques for evaluation of rewards of new action sequences, which we call policies in reinforcement learning nomenclature, using past offline data. And adaptive experimentation might refer to smart ways of collecting new data that may help in this estimation. So one thing about off-policy evaluation is that the success of off-policy evaluation techniques is based on how diverse is the offline data. So for example, if we haven't seen some of these states or actions, it's unlikely we will be able to make a good inference about that policy. Let me introduce two notions, recurrent states and transient states. So think of recurrent states as those states where they're modeling some frequent or consistent user behavior. For example, how a user interacts with the platform after the payday. Maybe they are more spending on the platform. And think of transient states as something that models transient, infrequent behavior. For example, how user might respond, the states that might transition to after a platform nudge. So intuition from a recent work in average reward setting, that's a recent work with Shipra, that shows that the optimal policy in average reward setting is the behavior of that optimal policy is dictated by the recurrent states. So this brings us to a question: can we improve the off-policy evaluation methods by relaxing the coverage condition required for it? And a good motivation would be this might help us in estimating or modeling long-term behavior. For example, churn rate across a month instead of a short duration. Now let's change gears a little bit. So A/B testing is one of the most widely used experimentation technique in practice. And so it's usually we want to run a test and a control case, and we think about how, and we divide the samples randomly and how the outcomes differ and take a decision whether the test was useful or not. But it's costly to run and may have lasting impacts. So the usual target is to run fewer and better A/B tests. And the proposal is, can we use the off-policy evaluation techniques to decide what A/B tests to run? And the proposed pipeline could be, if we have a good off-policy evaluation setup, and if we see good statistical results, can we design better A/B tests to run, fewer A/B tests to run? Well, on the one side, we have off-policy evaluation techniques aren't very great when you have unobserved factors affecting the state transitions of the rewards. And on certain conditions, we can design A/B tests which are robust against such confounding factors if we have enough data and other assumptions. So this gives a question, can we use the A/B tests to enhance the off-policy evaluation methods? And that's pretty much the summary of the talk here. So we have seen that off-policy evaluation methods are good when the confounding effects are limited. And in evaluating long-term performance of the policies, the expressivity of the off-policy evaluation methods may be enhanced. And given that we have good technical infrastructure to run huge amount of A/B tests, can we use them to enhance off-policy evaluation methods and vice versa? Thank you for listening, and thank you for having me here.
Okay, I think we'll skip questions, but Priyank promises to answer any of your questions during lunch hour. We don't want to hold you from lunch, otherwise there'll be a riot. So we'll just jump to the next presentation from Will Ma, who's an associate professor at the Graduate School of Business. Thank you.
Come on up. That's it.
All right. Hello, everyone. So I'm a faculty at the Columbia Business School. In a past life, I was also actually a professional poker player. So I was a consumer of these contests. Essentially, every Sunday, I would sit at my computer. I would join a schedule of these contests where, I was playing poker instead of trying to choose a fantasy sports team to bet on the current sports match. But conceptually, it's very much the same, which is why I'm very excited about what Dream Sports is doing. And, they're way ahead of the poker sites that I played on. Those were just very static, fixed schedules of tournaments that I could join. And here I'm going to present something about dynamic, state-dependent recommendation of contests. And this is also some problems I've talked about with Professor Vineet Goyal and Nilesh Patel at Dream Sports. All right, so a lot of the goal of our work is, we're solving kind of the same problem that we've already seen Shipra and Priyank talk about. A lot of what my research and the goals of this is to build sort of parsimonious, stylized models of the key trade-offs in this problem. So kind of coming from a complementary angle and trying to basically solve for optimal or approximately optimal solutions and seeing what those solutions reveal about the key trade-offs in the problem. So in this short presentation, I'm just going to give you the 3 key trade-offs that we aim to model, optimize, and then derive structure and understanding about optimal policies. Okay, so the first one is we're trying to be dynamic at responding to real-time demand predictions when it comes to matching supply and demand. So as Shipra already explained, there's contests and sort of there's a concept of both overlays and underlays. So I don't want to kind of create too many spots because if I do, then Dream Sports might lose out on money because these contests have guaranteed prize pools. And if you don't collect enough registration fees to recoup the guaranteed prize pool, then you run a deficit. But on the other hand, underlays are also a problem where if I don't generate enough contests with these spots, then there's going to be users who wanted to bet on the game and they couldn't find a contest to join. So this is actually classically studied in supply chain management as a news vendor problem. But what's very much new here is the fact that you have these real-time demand predictions that could change very quickly. Like let's say a star player gets injured, then the demand for the game might go down. You have to dynamically come up with these contests that sort of commit to a certain amount of spots with guaranteed prize pools. And it's sort of committal. Once I create the contest and somebody joins, I cannot uncreate the contest. And over time, as you can see in this cone of uncertainty, you sort of get finer and finer grained details about the final demand for that particular sports match. Okay, so that's the first trade-off. The second trade-off is we want to model how customers substitute between different contests. So let's say, by default, you have this contest on the left. And let's say you're thinking about, okay, let's create another contest where I have a lower entry fee and a lower prize pool. These are my really poor image editing. My graphics are much worse than what Shipra and Priyank generated using AI. So I really should have done that. But anyways, okay, so this is my manual $30 entry fee with a smaller entry and a smaller prize pool. Right. So if we create this, we might cater to a larger number of customers because there's people who don't want to gamble so much. They might want to prefer a smaller buy-in registration fee. But so we'll capture more market if we introduce more choice, but there's also cannibalization. Some of the people who might have been willing to pay 40 rupees might now switch to the 30 rupee or even smaller contests and not join the larger one. So then we actually lost out on revenue. So understanding this trade-off is a classical, what's called assortment optimization problem. And Dream Sports, given all the past data on customer choice, there's a lot of opportunity to also unveil new insights for this large literature on how customers make choices. Finally, the third trade-off that we will model is the state dependency of the problem. So generally, assortment optimization is studied where it's kind of a one and done thing, or you're selling assortments of like different products in, say, Amazon or Flipkart e-commerce. But here, you can model the customer state. And often what happens, as you see from this diagram that I think Nilesh made, is that customers can use money one-in-one contest to join another contest. So you can have very fine-grained predictions of when you might have this inflow because a match is about to end. Certain customers are going to win some money and then use it to join the next contest. So, and this is also what I did with poker often back in the day, where if I win some money, I could immediately join another contest. So being able to model users doing this is going to be very powerful and give users sort of the right recommendations. Okay, so that's it for the 3 trade-offs we're modeling. Thank you.
Since we're already over time, if you have any questions for Will, you can probably grab him during lunch hour now. But thank you very much. Can we have a round of applause still for all our speakers?